Oh.
Want some candy?
It's the only way you can keep the kids in his class.
Apparently knowledge is not good enough. I don't know if it's a good thing, or I mean, because I put the lectures online, and lots of students say they're just watching me online.
Yeah.
And you can watch it on TV later. You can see it live. Oh, I've had so much candy today. Candy? Are you in costume or just tie-dye and tights?
I'm a hippie.
You're a hippie?
Yeah.
Well, I knew that, but what's your costume?
I guess I don't have a costume.
I'm teasing it. I went to Berkeley, but I guess I'm not really a hippie.
Ooh. Well, you live on Valley,
What
yeah,
about Kauai? I mean, there's lots of hippies in Kauai too.
yeah,
You know?
that's true.
They're like the real hippies. It's like the ones at Berkeley are just kind of like burnt out, left over from the 60s.
Do you know if Election Day is a holiday we get off for school?
I think it's not.
Oh. Because the school calendar had it like marked down, but I'm confused.
Well, let us, even though we are recording now, let us see. Yeah, I guess it's on the academic calendar. November 6th. Yeah, Tuesday, holiday election day. Of course, this class meets on Monday, Wednesdays. But we, yeah. So we get election day and Veterans Day. Right here. So, yep. Okay. So let it be known online, students, you do not have to come to class on Tuesday, November 6th. So other questions? Given this stuff's not on the test, I'm actually happy that we're ahead. That means we can like spend a lot of time reviewing and studying for the final. But out of curiosity, how many people have had chemistry in high school? Oh, everyone did. Oh, so do you know how to do Lewis structures? Okay, well, you'll learn again today. So we're doing Lewis theory, and it's also Lewis theory. It's actually wrong. So teaching you lies today yet again, but it works well most of the time. So the real reason why things bond, so a bunch of atoms get together with their positive nuclei and their electrons, and they form new orbitals, and the electrons populate those, and if that's low energy, it'll work. If it's not low energy, it won't work. But Lewis theory works most of the time. There's only a few times it doesn't. Well, not a few times. It's the vast majority of the times it works. And for instance, I'm allergic to sulfa drugs, and if I ever get a drug, I always look up the Lewis structure, and I can tell from the Lewis structure if I'm allergic to it. So you look confused. Okay, I can show you.
Sounds great.
Show you. I will show you. So that's the structure right there. Yeah, there's a Lewis structure. And if you look at this group right here, now, like for instance, actually maybe I'll do a new tab. Oh, come on. Okay, here we go. So here's Celebrex, and notice you have the sulfur double bonded 2 oxygens, and then another attached to another carbon group. That's an amine. I don't. Can you see that? Yes, you can. So compare that to this. So you have this double bonded O attached to a nitrogen, attached to R means carbon, specifically hydrocarbon. So it's very similar to that. So I can't take Celebrex, for instance. Oh, R just means different groups. So and that's just organic chemistry terminology. It's like, but anyways. So it would fit. Let me look at the rest of Celebrex. It's not a complete R because there's nitrogens here, so it's close, and it's pretty close though. But which is why I'm not supposed to take it. Anyways, all right. Well, let me start the lecture talking about how to draw Lewis structures. Here's in the book, and I've gone ahead and made the rules even simpler. First rule for writing a Lewis structure is put down the skeleton. And some of the hints, put the biggest and or the least electronegative atom in the center. That goes in the center. And we're going to do simple molecules in this class. We're not doing the huge molecules. You don't have to, like Celebrex or sulfanamide. You don't have to write those structures. That's too big. So, and sum up the number of valence electrons, put octets on the outside, and then add double and triple bonds as needed to give the central atoms octets. And we'll cover this rule soon. Minimize the formal charge in general, and then if anything has to be negative, put it the electronegative atoms. And you're probably familiar, if you've had this in high school, you probably know the general trend here that hydrogen and halogens tend to form one bond, oxygen family 2 bonds, nitrogen family 3 bonds, and carbon 4 bonds. That's the general trend. Doesn't always work. And there is already a problem with Lewis theory. In fact, it's outright wrong. But in certain cases, like here in ozone, there's 2 possible Lewis structures. So they blend it together, kind of like saying if you have 2 dogs, that like if you have 2 dogs with different coloring, that the offspring is a blending of the 2. Kind of like the structure of 2 Lewis structures. So let me apply this. So what is the Lewis structure for nitrate? So first thing, skeletal structure. Nitrogen's going to be in the center, and there's going to be oxygens around it. Okay, so biggest, least electronegative atom in the center, oxygens around. Now we sum up the number of valence electrons. Nitrogen has 5 plus 3 times 6 for oxygen plus 1 for this negative charge. Where am I getting that valence electrons from? I'm counting 5. 1, 2, 3, 4, 5. And notice nitrogen's also group 5A. 6 for oxygen, group 6A. So counting over from left to right on the period. That tells you the valence electrons. So for nitrate, we have 24, right? So that's 24 electrons, right? So that's 4 times 6, which is 24. Now let's put electrons on the outside. Okay, so each line is 2. So I've already placed 6 electrons. 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So now I've placed all 24 electrons, and notice now I look to see if everything has an octet. Oxygens, they all have octets. Nitrogen only has 6, so it needs 2 more. And how do you get 2 more? Well, you erase one of those bonds and put a double bond there. But, and since this is an ion, you can put brackets around it and call it a -1 charge. But, why do I put it on there when I can? Why can't I do it this way? So why do I put the double bond there? Why don't I put it there? And likewise, why can't I put it there? And so I have the 3 resonance forms there, like so. But hopefully you're seeing the pattern though. Write the skeletal structure, put nitrogen in the center, because it's the biggest and least electronegative atom. Sum up the valence electrons, 24. Put electrons on the outside. After we do that, add the double bond to give nitrogen the octet. So, all good? Questions on how to do this? Okay. So, can you tell me which one's the proper Lewis structure for hydrogen cyanide? And the hint here is the number of electrons. So hydrogen has 1 plus 4 plus 5. So tell me which one of these has 10 electrons?
D.
Jumping the gun on me. Yeah, D is the right answer. It also fits carbon bonds of 4, nitrogen bonds of 3, and hydrogen bonds of 1. So 2, 4, 6, 8, 10. This one is a proper Lewis structure, 2, 4, 6, 8, 10, 12. That's 14 electrons. So this would be proper if it was -4 ion. The top one, A, would be a -2 ion. B is not good because hydrogen has a double bond. It usually only bonds with 1. Hydrogen can bond with more than 1, but that's a very, it's not, it doesn't happen very often. Happens with boron hydrides, also happens with hydrogen itself in a few strange circumstances. Nitrogen only has 4, it doesn't have the octet rule, so B that's a bad structure. You come in late, you gotta get candy. That's the rule. So, all right. So yes, it is B. Questions with this one? Okay. Now I'm going to talk about formal charge. So formal charge, to calculate formal charge, you look at half of the bonding electrons and all the lone pairs of an atom. Then you compare those number of electrons to its original number of valence electrons. Okay? So, quick example. Hydrofluoric acid. So, hydrogen normally starts with 1, fluorine normally starts with 7. So, hydrogen has 1 electron there, and so it has half the bonding, half of that single bond, so it gets 1 electron from that, starts with 1. The formal charge of hydrogen is 0. Fluorine gets 1 electron from that and has 6 from its lone pairs, so it has 7, starts with 7, formal charge 0. So both of these have a formal charge of 0. So let me do that to show you this example. So we want to know what the best Lewis structure is for OCN minus. So OCN minus, and I do apologize if anyone is colorblind because I put some colors on here to make it easier to see the electrons. So and to illustrate the formal charge. So oxygen starts with 6, carbon starts with 4, nitrogen starts with 5. Where am I getting that from? I'm getting that from this. Carbon is in group 4A. It is also 4 to the right from period number 2. So lithium, beryllium, boron, carbon, that's 4 spots. Nitrogen is 5, oxygen is 6. So that's where I'm getting the numbers from. And I have to decide between these 3 Lewis structures. Oxygen, as you can see here, the first atom has 6 electrons as lone pairs and 1 of the bonding electrons, so there's 7 electrons. Starts with 6, formal charge minus 1. Does that make sense? Everybody see the logic here? Carbon has 4 bonding, starts with 4, formal charge 0. Nitrogen has 3 bonding, 2 from lone pairs, so starts with 5, has 5, formal charge 0. This second molecule, so oxygen has 4 from lone pairs and 2 bonding, so starts with 6, has 6, formal charge 0. Carbon 4 bonding, formal charge 0, same as all. Nitrogen here has so 4 from lone pair, 2 from bonding, so it starts with 5, has 6, formal charge minus 1. Now over here, oxygen has 2 lone pairs, 3 from bonding, so starts with 6, has 5, formal charge plus 1. Carbon for 0. Nitrogen, so 6 lone pairs, 1 bonding, so starts with 5, has 7, formal charge minus 2. And so now we have to minimize formal charge. So obviously that one gets cut because it's got a minus 2. The other ones have minus 1. So we have to pick between these two, and we pick this one because oxygen is more electronegative than nitrogen. So the electrons are more likely to be around oxygen than they are nitrogen, so we're going to pick this one as the proper one. Does that make sense? So you following the logic? Okay. Good. So what is the formal charge in the central atom in ozone? So the central oxygen atom in ozone, there is the structure for ozone. Oxygen normally has 6 valence electrons. So what is the formal charge of the center one? This one right here. How many think A 0? How many think B plus 1? How many think C minus 1? How many think D minus 2? Okay, so you guys are stuck. Let me show you the electrons that are around it. So it gets 1 from each of the bonds, gets 2 from the lone pair. How many electrons is that? Do I have to do Sesame Street on you guys? 1 electron. Ha, ha. 2 electrons. 3 electrons. 4 electrons. 5 electrons. How many does oxygen start with?
6.
So, is it then? It's plus 1.
How do you tell if it's plus 1 or minus 1?
So, extra electrons means extra negative charge. So, more electrons is a negative charge, fewer electrons is a plus charge. Same thing with any ion. So, other questions? You guys watch Sesame Street, or am I?
No, that's perfect.
Okay. Okay, good. I don't know how I'm getting older, and people are some of my references are going away. I just don't know how to communicate anymore. Okay, so what would chemistry be unless I talk about the exceptions? So we have some exceptions to the octet rule. We have 3. We have odd electrons, we have incomplete octets, and we have expanded octets. So let's start with the odd electrons, and I'm also hoping you'll watch me do Lewis structures, and then you'll kind of like, oh, this is how you do it. So let's start with nitrogen monoxide. Nitrogen has 5 electrons and then 6 from oxygen, so we have 11 electrons. And the Lewis structure is this. So we have just 2 atoms, so you have to pick. It's just they're just bonded to each other. So 2 electrons are at the bond. 4, 6, 8, 10, 11. And oxygen has an octet. As drawn, nitrogen has 5 electrons, right? 1 or 2 from the bond, 3 lone pair, so that's 5. So what can happen is we can turn one of those lone pairs into a double bond, and we just have an odd number of electrons. But if you look at the formal charge, nitrogen 1, 2, 3, 4, 5 has 5, starts with 5, formal charge 0. Oxygen 1, 2, 3, 4, 5, 6 starts with 6, formal charge 0 there too. So, but that's the best Lewis structure for that, because it's a formal charge of 0. If the formal charge is 0, you've got a good Lewis structure. Unless it's what's called an isomer. An isomer is the same number and type of atom, but different connectivity. And of course, for a diatomic, there's only one way that it would be able to be joined. Also for NO2, so we have 5 plus 6 times 2. That's 17 electrons. And this is going to be like this. So nitrogen in the center. And so we have 4, 6, 8, 10, 12, 14, 16, 17. Same deal. One of these becomes a double bond, and then there'll be a resonance of the other structure. Like so. But again, it's odd number of electrons. And it turns out that free radicals are very reactive. So they exist, and they're very reactive, and they also, among other things, they can propagate chemical reactions. And a chemical reaction many people are interested in is fire. So, has anyone ever heard of the fire triangle or the fire tetrahedron before? Haven't heard that, okay. So, this is basic fire science. Used to be the fire triangle, now it's the fire tetrahedron. Fire triangle is that a fire is caused by fuel, oxygen, and heat. If you remove one, the fire goes out. So imagine a campfire. If all the wood burns away, all the fuel is gone, fire goes out. What if I have a candle and I put it into a jar or something like that, close the lid? What's going to happen? The oxygen will get burned out, the candle will go out, right? So loss of oxygen will blow out the fire. Last one is heat. So imagine your campfire. What happens? You can put out a fire by throwing water on it. What happens when you throw water on a fire? Makes steam. Makes steam. What is happening? It takes the heat away. Fire goes out. So the fire tetrahedron is the same thing, but it adds a fourth side. Instead of oxygen, it says oxidizer. So chlorine, for instance, chlorine, you can burn things in chlorine. So it doesn't have to be oxygen. And the last step in it is a chain reaction. So you can put out a fire by blocking the chain reaction. And there are certain chemicals called halons. And halons are chemicals, when they heat up, they release halogens, hence the name halon. And has anyone ever seen one of the best movies ever made, Terminator 2? Do you remember when they're in the Cyberdyne systems and they blow up the door, and then the halons come down like, oh, it's the halons, and then they have to grab gas masks? You remember that part? No, you don't. Okay. I don't think there's time to search for it, but in the movie, they blow something up in the Cyberdyne systems, and then the fire extinguishing system releases halons. And what halons do when they heat up, they release halogens, and the halogens react with the free radicals, and it puts fires out. So they had to grab gas masks. Halons are safe, but they displace oxygen. So like if you go somewhere and You ever seen the show 1,000 Ways to Die?
Yeah.
There was these people went into this big helium container and they were playing around but then they suffocated because the helium they were breathing but they couldn't get any oxygen. So that's what halons can do that. So if you breathe in halons, you can suffocate that way. But so that's why they were hiding until Arnold came back with the Terminator, the T-800 brought the gas masks. So, but one way of fire extinguishing fires. Okay, incomplete octets. So let's look at this. Boron. Boron has 3 electrons and 3 times 7 for fluorine. This is 24 electrons. Just to put a point home, boron is here, group 3A, 3 over from the right. Fluorine is group 7A, 7 over from the right. I'm sorry, from the left, moving to the right. So that's where the electrons come from. So boron in the center, and then fluorine's around it. Oh, shoot. And I got, Facebook too. Nice. There are more embarrassing things that could have appeared. So, okay. Back to chemistry and not Facebook. Which I, of course, look through for scholarly activities, by the way, which is one of my primary functions as a faculty member at the University of Hawaii, Maui College. So, boron trifluoride, boron is in the center with 3 fluorines attached to it. So 3 lines, 6 electrons, 8, 10, 12, 14, 16, 18, 20, 22, 24. So all 24 electrons. And you were saying, why don't I do the double bond and then that and then have a resonance form? It turns out for boron trifluoride, it does not do that, just sits with an incomplete octet. And this molecule also happens to be very reactive. So it will react. It can form an octet, but fluorine is too electronegative. It will not give its electron density back to boron. Same thing with aluminum trichloride. Aluminum is just under boron, and then chlorine is under fluorine. So we have 24 electrons, and we have aluminum in the center, Cls as such, and you're like, wait a second, aluminum is a metal, and chlorine is a nonmetal. Well, guess what? Metals can bond with nonmetals in a covalent fashion. Metals can also bond with metals in a covalent fashion. So some of those things you learned are incorrect. And we'll talk more about that in the next chapter. So it's really just going to be the same. So 6 electrons placed, 8, 10, 12, 14, 16, 18, 20, 22, 24. So aluminum trichloride. Okay. Everybody answer our questions? Expanded octets. And we will do lots of practice with this. There's going to be a lab on this as well to look at some Lewis structures. But for expanded octets, it only works for period 3 and beyond. So periodic table, the periods are the rows. Period 3, sodium on. So if you look at something like phosphorus and sulfur have electrons in the 3s and the 3p. They don't have any in the 3d, but the 3d is there but available. So we'll learn later that the availability of the d electrons and the empty orbitals, those can then be filled, in which makes the structure bigger. Whereas carbon is only in the second quantum shell, the 2p. There is no d orbitals in the 2, and the n equals 2. So has to have empty d orbitals, which is group 3, or has availability for d orbitals. So period 3 and beyond. So let's look at phosphorus pentachloride. So phosphorus is 5. So 5 electrons just underneath nitrogen, plus 5 times 7. So that's here, that's 8 times, that's 40. 40 electrons, right? So that's, wait a second. 5 times 8, yeah, that's right. 5 times 8, that's 40. All right, so phosphorus in the center, and then we have 3 or 5 chlorines, like so. And so I have 5 lines, that's 10 electrons, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. So all electrons placed, and I've purposely drawn the chlorines this way. You'll find next chapter, which won't happen until after the next test, but this is known as a trigonal bipyramidal structure. So we'll learn about that next chapter. But each electron is placed, and phosphorus can have the expanded octet. Same thing with sulfur hexafluoride. So sulfur hexafluoride is 6 from the sulfur plus 6 times 7 for the fluorines. And so 6 times 7 is 42 plus 6 is 48 electrons. So sulfur in the center, fluorines all around and above and below. I'm drawing it this way because it's a octahedral structure, which we'll learn next chapter. So I've drawn 6 lines, 12 electrons, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. So 6 lone pairs around, or six electrons, 3 lone pairs around each fluorine, and then the bonded line. So sulfur has an expanded octet, has 12 electrons around it, but it can handle that. And sulfur hexafluoride is an interesting molecule because it's part of our stealth technology. So our stealth technology is threefold, so which is not classified, by the way. The first is the material that the stealth planes and/or marine craft are made of absorb microwaves. So the way radar works, so you have an airplane, you have a radar station, you shoot it with microwaves, it hits the target, it gets bounced back, and from the delay you can figure out from where it is. So number one, the craft just absorb microwaves. So it is a bunch of different layers. What the layers are made of is not classified. The thickness of the layers is classified. So they just absorb microwaves. Number two, they're angled in such a way. So the stealth bomber has really angular looking shape to it. So if you have an angle and the microwaves come, they get reflected like bing out. So when it pings, it just reflects it out away from the aircraft, and you can't track where it is. The stealth fighter, the Raptor, it's very smooth. It has a different. It's not necessarily it's angled, but it's a little bit more of a sleeker design. It's more advanced. The last part is the fuel. So we have very clean fuel in the stealth fighters because one of the easiest ways to track an aircraft is not the aircraft itself, but the soot trail behind it. So when you burn the jet fuel, there's lots of soot in it, and then you can you can look at the radar signature of the soot coming off. Like maybe you've heard of a heat-seeking missile before. A heat-seeking missile is not seeking heat. It's a radar fix on the soot trail of an aircraft. So it's actually seeking out the soot. So what's the point of having an aircraft that's invisible itself if your exhaust is visible? So what they do, among other things, they add sulfur hexafluoride to the fuel mixture. So when the fuel burns, fluorine pops off, and as it's an electron scavenger. It attacks free radicals. And because of that, the exhaust coming out of a stealth fighter is very, very clean, has no soot in it. And so because of that, it's very hard to track. And so you'll see pollution reports of things. Here's sulfur hexafluoride right here. It's a gas, but it's a very heavy gas. But you'll see pollution reports. You'll see published like, oh, there's sulfur hexafluoride. Like, hello, United States. Why is there sulfur hexafluoride there? It's because we've been flying our stealth fighters there. So they don't know where it is, but they know after the fact because they can see it from our exhaust. And it floats down. So I mean, like it's heavy stuff. So after it leaves the fighter, it'll sink down, much like that. So it's kind of, so you see if they have aluminum foil there, you can make a boat out of it, and you can float it on top of sulfur hexafluoride. So yeah, part of our stealth technology. Who would have thought? Okay, so let's do an example of this. Write the Lewis structure for xenon difluoride. So xenon is here, and it has 8 electrons. Fluorine is here, and it has 7 valence electrons. So xenon difluoride, it's going to be 8 electrons from the xenon plus 2 times 7 for the fluorine. That's 22 electrons, right? So 14 plus 8 is 22. And the structure is going to be the big atom in the center. So I have 2 lines. That's 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So 22 electrons around, or sorry, the 10 electrons around the xenon, but the fluorines all have octets. So xenon can have the expanded octet because it is period 3 and beyond. So, do you see the procedure, how I'm doing this and thinking? So how are we doing? Questions with this? You'll have much more of a chance to look at some more stuff later. Okay, so next thing I'm going to do is talk about average bond energies. So let's, in the bond energy, this is the amount of energy it takes to break a bond. So remember I mentioned this with people. Like if you just met someone and I say, hey, if I give you $10, you agree never to talk to this person again? Like, oh, sure, why not? If you've known each other for a while, like, I don't know, my price has gone up. I like this person. Maybe for 10,000, right? So instead of money, to rip atoms apart, you have to add energy. And the more bonded the atoms are, the more energy it takes. So if you look at this, so when I say average bond energies, let's look at these 2 hydrogen-carbon bonds. This bond here on methanol is weaker than methane because there's this oxygen here. What happens is the electron density flows towards this oxygen and makes this bond weaker. So it's easier to break this bond than that bond. So, but what we've done though, I don't know, I didn't do this, but what they've done is they've taken the average bond energies and just looked at a bunch of them and say, all right, well, the average bond energy of a carbon-hydrogen bond is 414. So took a bunch of bonds and then measured them and added some sort of average to them, like so. And then we can estimate a chemical reaction by the number of bonds broken minus the number of bonds formed. So remember thermo, putting energy into the system is positive. So it takes energy to break a bond, so that direction is positive. And then when bonds are formed, energy is released. That's the negative direction. So you can use this to calculate the heat of reaction. So let's look at this. So hydrogen can be made this way, and for one of the rare occasions, this is actually how we make hydrogen. We make it by steam reformation or one of the ways we can make it is like this. So let's draw this structure. Well, it helps to draw the Lewis structures. So carbon has 4 electrons, and hydrogen has 1 electron, but there are 4 of them, so we have 8 electrons for this. So carbon in the center, and then hydrogen's around it like so. And so we have 8 electrons, and with these 4 lines, we've placed 8 electrons, and it's our Lewis structure's gone. Water, we have 2 times 1 from the hydrogen plus 6 from the oxygen. We also have 8 electrons, so we have oxygen in the center with 2 hydrogens there. So 4 electrons are placed, 6 and 8, and all electrons are placed, so we're done. Hydrogen, this one is just, I don't even know if I want to explain that one. It's just 2 electrons, 2 atoms, 1 bond. Carbon dioxide, there are 4 electrons from carbon plus 2 times 6 for our oxygen. That's 16 electrons. So we have carbon in the center, oxygen, oxygen. So 4 electrons, 6, 8, 10, 12, 14, 16. Carbon, oxygen has an octet, carbon only has 4. So we can add double bonds to get it to 8, like so. So there's CO2. Okay. Does anybody have any questions on how I drew the Lewis structures? So I'm going to just go ahead and write the chemical reaction this way. Okay, so bonds broken minus bonds formed. So what bonds are we breaking? We are breaking 4 carbon-hydrogen bonds. And, oh, okay. So 4 carbon-hydrogen bonds. I apologize again if you're colorblind. And we're making 4 oxygen-hydrogen bonds. And we're subtracting 4 hydrogen-hydrogen bonds. And 2 carbon double bonds. Like so. So does everyone see that in the number? Do I have to break out the count again? All right, so we just have to put in the numbers. You won't have to memorize any of this stuff. So here is carbon, hydrogen, that's 414, 414, plus 4 oxygen, hydrogen, 464, minus 436, and I can already see 799. I can already see the 799 in CO2 for that. So if you put that in your handy-dandy calculator, you get this equals positive 170 kilojoules per mole reaction. Okay. So do you see this? You can estimate, now this is an estimate, estimate the amount of energy of a chemical reaction by drawing out the Lewis structures of the reactants and the products, and then looking to see what type of bonds are broken and formed, and then add them up and then get the overall energy. And so why do we care? If you're working on this, say that you're an engineer working on this, and you know, like, okay, this reaction vessel, is this going to be exothermic or endothermic? That way, in this case, it's endothermic. It's positive. So I can do one of 2 things. I'm more likely going to heat it up. I'll probably say, okay, I need to put a heater here because it's going to draw energy away from something. So, and I want to keep the temperature high so it reacts. You could, if something is also cool, you could say, well, maybe I can do something else, if I need to have a heat exchanger somewhere. What if I just ran the pipe by this, and then I could use the cooling effect of this reaction to save energy somewhere else. So that's another thing you can do. So that's the so what. Okay, let's see if you can do this. What is the heat of formation of ammonia from hydrogen and nitrogen based off of these average bond energies? And I have taken the liberty of drawing the Lewis structures there. They're here. Here are the average bond energies right there. I have so much chocolate. Ooh, there's the Milky Way. What? I like caramel. Or caramel, or however you want to say it. I guess I just like sugar. I think I'm so hyper today. I'm eating lots of candy. I even took a nap. I was like hyper and I like crashed. Like being a little kid again. There's your hint. And I'm not gonna. It's kind of like you ever play those trivia games on like the bars or something? Or you guys are too young to go to bars. Yeah. And they have like the hints. And then the selections go away. The thing that people have a hard time with of this one is that there's 6 hydrogen-nitrogen bonds. There's 2 of these. That's the most common mistake. But if you add it up, it's negative 80. Questions with this? Okay. So we're going to get out early. We might get 15 minutes out early today. Last class, the first class went out early too, about 5 minutes. Okay. So, I use people analogies a lot. People and molecules are very similar. So, people that you really like, you tend to be closer to. You even use words to indicate that. So, me and my brother are very close. This is my close friend. This is my acquaintance. So and you can kind of tell by people's body language, specifically how close they are to each other, how much they like each other, right? So if you're like, "Good to see you, man. High five," that kind of thing. That's you're like, that's someone they don't like each other that much. And if you're like, "Oh, haven't seen you. Has it been like yesterday? You know, give me a big hug." You're like, "Oh, they're close to each other. They're very bonded." So things that are bonded tend to be closer. So here's carbon with a single bond length of 154 picometers, double bonded 134, triple bonded 120. So the more strongly bonded, the closer they are to each other. This comes at a limit, though, right? Because also, well, let me back up. There's, you're gonna learn a lot in chemistry class today. Basic flirting techniques 101. If you like someone, get closer to them. You're like, I like that girl, right? That doesn't work as well usually. It's like, oh, and if you start talking to someone and then you kind of, get a little closer to that person, that's indication that, and see what happens.
Not too close, though.
Oh, there we go. There we go. That is the problem. And molecules are the same way. So, right? Because, this is kind of an acceptable distance, but if you start getting, really into someone's face, you're like, you're in my face. I don't like this. Molecules are the same way. Because, so as two atoms approach each other, they're like, okay, this is a comfortable bond distance. This is comfortable. Oh, that's uncomfortable. Why is it uncomfortable? Because atoms have nuclei, and they're positively charged. If you get too close, then the positive nuclei start to repel. So, it's not like things will just bond super, super close. And so thank you for the clarification. Yes. And again, but molecules already know that. So, yes, there's a happy medium. And some other things to note. So we have hydrogen here, bond length 74 picometers. Iodine here, bond length 266. So why is it so much bigger from hydrogen to iodine? Because iodine's a bigger atom. And also with the closeness effect, iodine has a very positive nucleus. So as it approaches, there is a repulsion from the nucleus as well. So hydrogen has a tiny +1 nucleus. Iodine, I don't know its number. It's going to have a very positive nucleus. Now I want to know. I don't have its 53 protons. So it has a plus 53 center. So generally speaking, the closer two atoms are, the more strongly bound they are. So, but what would chemistry class be unless I had an exception to that rule? There is an exception to that rule here with the nitrogen-halogen bonds. So if you look here with the bond lengths, they get bigger. So the nitrogen attached to the halogens, they get bigger as they go down. So because the atoms are getting bigger. And you would expect the bond energies to also go down, except you see here nitrogen-chlorine is a lower bond strength than nitrogen and bromine. So it's a general trend, not a smooth trend, because chemistry, among other things, is an observational science, and we can only report what we observe. So can send the complaints to whoever created the physics, I suppose. But, okay. So we are done then. Anybody have any questions or anything? So this is not on the next test, but it'll be on the final, but we have lots of time to cover all that stuff, so we're going to end class a little early. So thank you all 5 for coming today, and let me stop the YouTube video.